Chapter 8, Section 2. In the previous section, we learned how population distribution can be interpreted through density functions. This section will allow us to present the same information in a different manner. Here, we're going to be looking at what's called a cumulative distribution function, often notated CDF, in probability. So the cumulative distribution is the antiderivative of the probability density function that we just looked at in the last chapter. Therefore, sketching the derivative of the graph of a cumulative distribution function will give you the density function graph. So here, if we have a PDF, a density function, the area under the density graph's curve between 0 and t is going to be represented by the CDF, the cumulative distribution. What does this look like? So for example, we're going to look at the values of how much area we've accumulated up to a certain point. So when time equals 0, we haven't started yet, so we have no area. When time equals 20, what this says is that we've accumulated 29% of the area when we get to 20. So that means that 29% of the data falls between 0 and 20. When we get to 40, that means we've accumulated 58% of the data. So from 0 to 40 represents 58% of the population. When we talk about 60, we talk about all the area under the curve that's accumulated until 60. So that's 84% of the population. When we talk about 80, since it's 0.97, that means that by the time we get to 80, for whatever our function is, we've accumulated 97% of the data, or the area under the curve. And by the time we get to 100, it equals 1, which means by the time we get to 100, we end, because we now have hit the maximum, which is 100% of the population. So basically what we're doing is we're calculating how much of the area has been added up from the PDF. So what does the general form look like? So since it's the antiderivative, what we're doing is we're taking the integral from negative infinity up to t. Now, negative infinity is just the general form. Usually we start around 0, so it's whatever your starting point is up till t. And that gives us the fraction of the population having values of x below whatever t is. So again, capital P is the antiderivative of little p, and if you were to take the derivative of the CDF, you would get the PDF back. Some of the properties of the cumulative density function is that p is increasing, so we're always accumulating area. As t goes to infinity, the CDF becomes 1, because eventually we have the entire population. And if you go backwards towards negative infinity, it's going to go to 0, because we had to start somewhere. So again, the fraction of the population having values of x between a and b, we can use the fundamental theorem of calculus. It's going to be the difference between the CDF at the upper bound minus the CDF at the lower bound. So let's look at an example with a table. The cumulative distribution function for time it takes a student to finish a calculus exam. So at time 0, 0% have finished. At time 10, 12% have finished. At time 20, 27% have finished. At time 30, 45% have finished. At time 40, 82% have finished. And by 50 minutes after the start of the exam, 97% of the students have finished the exam. So, how can we ask some questions and read the data? So for part A, what percentage of the students finished the exam in 10 minutes or less? So that's everything from 0 to 10 minutes. Well, at 10 minutes, 12% of the students have finished the exam. Remember, 0.12 is the same thing as 12%. For part B, what fraction of the students have completed the exam between 10 and 20 minutes? Well, between 10 and 20 minutes doesn't count all the students who finished before the 10-minute mark. So we want to use the fundamental theorem of calculus. So we're going to do the CDF at 20 minus the CDF at 10. So the difference between these two fractions completed. So we do 27% minus 12%. So that tells us that 15% finished between 10 and 20. So the subtraction should make sense, especially with that word between. In part C, what fraction of the students complete the exam in more than 50 minutes? So we know that at 50 minutes, 97% have completed it, And we want to know how many took more than 50 minutes. So since we know that eventually the CDF reaches 1, we're going to do 1 minus the CDF at 50. So if you do 1 minus 0.97, we get that 3% of the students took more than 50 minutes. And that should make sense because whatever we add to that will get us to the total, which we know has to be 1. So for our example here, we can sketch a brief little graph of what the CDF is going to look like. So at time 0, 0% have finished, so we have 0, 0. Then we have the point 10.12, 20.27. We're just plotting these data points, and what we see is that the CDF is increasing, which we expect, that it's approaching the number 1, so these y values are getting bigger, and if you go backwards, they're going to approach back towards 0. So we can see that the y value represents the percentage or fraction completed for each time. Now using the data, we can create a chart showing the percentage completed for each value of t in time intervals, because as we said before, sometimes it's better to break it up into intervals. So some of the data we can get from this is if we wanted to find the percentage of students that took from 0 to 10 minutes. Well, we know that between 0 and 10, we would do 0.12 minus 0, so 12% finished between 0 and 10 minutes. From 10 to 20 minutes, well again, from 10 to 20 means we want to take the difference between these two fraction completes. So 0.27 minus 0.12 tells us that 15% of students finished between 10 and 20 minutes. Between 20 and 30 minutes, again, we're going to subtract these two numbers here to get just the 10-minute interval here. So 0.45 minus 0.27 gives us 18%. From 30 to 40 minutes, we're going to do 0.82 minus 0.45. So that tells us 37% of students finished between 30 and 40 minutes. From 40 to 50, we'll do 0.97 minus 0.82, which gives us 15%. And greater than 50, so more than 50 minutes, we said before, was 1, which is going to be our ultimate endpoint, because CDFs, the highest value they can take is 1, minus the 0.97, which gives us 3%. Now if you were to add up all these percentages, it would add up to 100%. But now we found a way to break this up into intervals. We can also take these intervals now and put them in a table of their own. So here, this represents the data we just found. So it took from 0 to 10 minutes, 12%. From 10 to 20 minutes, 15% took that long. 20 to 30 minutes, 18%. 30 to 40 minutes, 37%. 40 to 50 minutes, 15%. And greater than 15 minutes would be 3%. So we can chart it this way, and again, you can create a rough chart of what these numbers will look like, and this is going to be an approximate representation of our PDF, the density function, that we started with to integrate to get these numbers in the first place. So again, this is also an approximate sketch of the derivative of the CDF. So if we were to pick a value at random from a cumulative function, how could we find the probability that it'll fall between 2 points that we choose? Well, if you have a density function, so if you start with a PDF, then the probability that a population is between A and B is going to be the probability that the fraction of the population is less than t. So we would look at the area under the curve from A to B. We did this in the last section, mostly approximating with graphs. So again, with the density function, you're looking for the area under the curve between these 2 points. Now, for the CDF, for the cumulative distribution function, we're asking the question, what is the probability that a population is less than some value of t? So again, we're usually starting at the start point and going up to some value t. So the fraction of the population less than t is represented by the integral from 0 to t of the PDF. So for example, let's look at a quick graph. Find the probability that the number we choose will fall between 2 and 4 using the following density graph. So the idea here is that our density graph is defined from 2 to 8. And we're going to ask someone at random to pick a number between 2 and 8. And we want to know what the probability is for each of these intervals. So here we want to know what the probability is that the number that is chosen randomly will be between 2 and 4. So as we said before, what that means is we want to know how much area is under the density graph from 2 to 4. How do we do that? Well, the first thing we want to do is calculate the area of one square. So here, let's look from 2 to 3. So that's going to have a base of 1 and a height of 0.04. So the area of one square is 0.04. Then we want to approximate how many squares there are under the graph from 2 to 4. So I count 1, 2, 3, 4, 5, and then 2 half squares, which would make 6. So the probability is going to be the area under the curve from 2 to 4. So approximately 6 squares, each having an area of 0.04, gives me a 0.24 percentage. So there's a 24% chance that if someone were to pick a number at random between 2 and 8, that it will actually fall between 2 and 4. So what we want to do is we want to look at the probabilities all the way from 2 to 8. So the probability that they were to pick a number between 2 and 3, per se, would be 1, 2 and a half. There's 2.5 blocks from 2 to 3, times 0.04, which would give us 10. The probability that's going to be from 2 to 4, we said was 24%. If we wanted to do 2 to 5, we would count those blocks, so on and so forth. I've done that for you and put it in a chart so we don't have to do it. But what we want to look at again is how many blocks there are between the starting point of 2 and each ending point, 3, 4, 5, 6, 7, 8. So here, I've created a chart. So between 2 and 2, there's no area because we don't move. That's 0. Between 2 and 3, we said it's 0.10 because there are 2.5 blocks times 0.04. Between 2 and 4, we found the percentage to be 0.24. And then I've calculated the rest. Between 2 and 5 would be 0.42. Between 2 and 6, 0.64. Between 2 and 7, 0.85. And between 2 and 8 would be 1. So what this tells us again is that the probability that if we pick a number at random between 2 and 8, that it'll be between 2 and 8 is 100%. So that makes sense. The probability that the number will fall between 2 and 4 is 24%. So again, now this represents the CDF. So we can plot each of these numbers, and again we see it's increasing. We plot these as our y values. We see that it approaches 1, and if you go backwards in time, it goes back towards 0. So using CDFs instead of PDFs, the probability that it falls between 2 and 4, we use the fundamental theorem of calculus. We would do the probability at 4 minus the probability at 2, which is 0.24 minus 0, which is still 24%. So we get the same answer. So if we have a chart of just the CDF, we can still find the answer that we were looking for before by looking at the difference, okay, between these two fractions when we're given a table. Whereas if we started with the PDF, we want to look at the area under that curve. So you should take some time to look at the other examples that I've posted in the other video of CDFs and what we can do with them.